Hello, everyone. My name is Hannah Turner, and I'm the president of the Marshall University Astronomy Club, MUAC. I thank you all for joining us for our Fall 2024 virtual speaker series. Drawing inspiration from our sister organization, the Society of Physics Students, or SBS, which utilizes their series to spread science knowledge to the public, MUAC has created this series with the intent of capturing a glimpse into the minds of astronomers from our surrounding communities. A fundamental goal of MUAC has been, and always will be, to encourage astronomy discussions among upcoming generations. When we provide a platform for such knowledge to flourish, we aid a sense of possibility to all children within our local communities. Becoming an astronaut, an astrophysicist, or even a leader of a university astronomy group doesn't seem so impossible. I speak for all leading MUAC members when I say that we are very proud of what we have accomplished with this club. With that being said, I would like to introduce MUAC advisor, Dr. Sean McBride.
Thank you, Hannah. Uh, I'd like to reiterate what Hannah has said. I'm very proud of the students and what they have accomplished with this club so far. So as Hannah mentioned, my name is Dr. Sean McBride. I'm an associate professor in the Department of Mathematics and Physics here at Marshall. I first want to thank Hannah. She has done a stellar job with this, organizing this speaker series. She's really taken the lead to reach out to professors and connect with them and to schedule the talks. She's done a really amazing job with this speaker series. So thank you, Hannah, for all your hard work and organization skills for this. So like Hannah said, and like I said, I'm with the math and physics department here. So that's how the astronomy club is tied to a department here at Marshall. Our department is a vibrant community of scholars who are passionate about exploring the fascinating intersection between mathematics and physics. In the mathematics program, there's probably well over 20 faculty members. And in the physics program, we have 8 faculty members. There's undergraduate programs in mathematics, physics, and statistics. And there's graduate programs with a mathematics MA, a physical and applied sciences master's, and a focus in physics master's degree. So Marshall's often described as just the right size university. So we have excellent student to teacher ratios of about 17 to 1. So average undergraduate class size is about 20 students, and average graduate class size is about 10 students. So overall, there's about 8,300 undergraduate students, about 2,400 graduate students, and about 550 students in professional programs like the MD program and PharmD program. And just another fact, about 86% of our faculty have a terminal degree in their field. So if you have any questions about Marshall, please feel free to reach out to Hannah or myself. And if we don't know the answers, we will guide you to someone that will. So if you're interested in maybe physics or astronomy, please contact me. My email is easy. It's my last name, McBride, and then S, so MCBRIDES at marshall.edu. And just email me any questions, even if it's not a physics or astronomy interest that you have. I'm willing to help guide you in the right direction for any major that you're interested in or any question that you have. So if you're interested in the topics that you hear tonight, please do feel free to contact our speaker. I'm sure he'd be more than willing to address any questions that you have as well. And with that, I think I will properly allow Hannah to introduce our speaker.
Very well said. Thank you. So without further ado, it is my utmost pleasure to introduce our second speaker in this series, Dr. Paul Martini, who will be speaking to us this evening on Unraveling the Mystery of Cosmic Acceleration. This talk will span 45 minutes approximately, followed by a 15-minute Q&A period for all of our listeners to send questions within the live chat. We do ask that everyone hold their questions until the end. Dr. Martini?
Thank you very much. It's a great pleasure to be here, and thank you for the introduction. I will share my screen and get started. Okay. I'm excited to join you today to tell you about the nature of cosmic acceleration and a new scientific instrument called the Dark Energy Spectroscopic Instrument, or DESI for short. I helped to build the instrumentation for DESI over the course of about 5 years. And then for about the last 3 years, I and hundreds of other scientists in the DESI collaboration have been using the instrument to conduct a new survey of the night sky. And this survey is just really amazing. I'm really excited to tell you about it. It is something that has dramatically surpassed all previous projects in terms of the number of objects it has observed, and it's done that in an incredibly short period of time. Furthermore, our recent release of data and analysis from the first year of observations has already offered some tantalizing clues about the mysterious nature of cosmic acceleration. Before I tell you about these results more, though, I want to tell you a little bit about the background image for this title slide. I picked it for two reasons. One is that it really captures the impressive structure that houses the telescope. DESI uses the largest telescope at the Kitt Peak National Observatory in Arizona, which is near Tucson. This is the 4-meter Mayall telescope, and you can see that it appears to tower over both other telescopes and the nearby mountains. I've stood next to this telescope many times and also observed from this building many times, and it is really an impressive structure. The entire observatory, from the ground level to the tippy top, is about equivalent in height to an 18-story building. And the ground floor for the telescope, which is located about here at the base of the dome area, is about 120 feet above the ground level. Yet I also chose this photo because it captures some of the beauty of the sky at night. And I think one of the most romantic aspects of astronomy is spending the night at a telescope, usually on the top of a mountain in some secluded location, like the one you can see here, and staring up at the night sky and pondering just the sheer size of the cosmos relative to humanity's very small place within it. And this contrast is really humbling, no matter how impressive the telescope and the mountain may be. Oh, sorry. To better capture this point, I'd like to share with you a small anecdote about the immensity of the universe. Many of you may have heard of the New Horizons mission to Pluto, which was launched back in 2006. At the time, the New Horizons mission was the fastest spacecraft ever launched from the Earth. And when it flew by Pluto 10 years later, it was traveling at about 32,000 miles per hour, or 14 kilometers per second. This is amazingly fast, and yet it still took 10 years to get from the Earth to Pluto. Furthermore, if it continued at this speed, it would take nearly 90,000 years to reach even the very nearest star to our own. And the objects that I'm going to be talking about in this presentation are millions to billions of times farther away than that. So I hope that gives you some sense to start off on just the sheer scale of the cosmos that I'll be talking about today. Yet actually, it was neither the beauty of the night sky nor the vastness of the universe that really got me excited about astronomy in the first place. Instead, I was really attracted by the possibility that we can use observations of the night sky to study physics and to answer questions about the universe, even though the objects that we study are millions to billions of light years away, and therefore that they must have emitted their light, the light that we see today, millions or even billions of years ago. Just a very fascinating concept that really got me excited from when I was quite young. One really early application of this idea that predated my birth by many decades was the use of astronomical observations by Edwin Hubble and Edwin Hubble's discovery that more distant galaxies are receding from us more rapidly. This figure shows the key result from Hubble's work back in the 1920s, so almost 100 years ago now. This particular figure was published in a seminal paper of his in 1929. The bottom axis shows the distances to various galaxies that he had studied. And these are distances measured in parsecs, where a parsec corresponds to a little more than the distance that light can travel in about 3 years. So for instance, the nearest star to the Earth is a little bit more than a parsec away. And yet the galaxies on Hubble's diagram are labeled in distances of millions of parsecs. So these are millions of parsecs away from, these are millions of times farther away than the nearest star. And they're much larger than our entire galaxy. The vertical axis on this figure is the recession velocity, how fast the object is moving away from us. And this is in units of kilometers per second. These are 500 to 1,000 kilometers per second. And these velocities are also huge. They are way larger than New Horizons speed of only about 14 kilometers per second when it passed Pluto. So more than an order of magnitude larger, nearly 2 orders of magnitude larger than the fastest spacecraft ever launched from Earth. The light waves from these objects are moving away from us, and because of this moving away from us, they are shifted to longer wavelengths by the Doppler effect. The Doppler effect for light works similarly to the way it works for sound waves. For sound waves, I think we've all probably heard a siren speeding by, and as it shifts to moving towards us to away from us, we can hear the frequencies shifting to lower frequencies. For light, it is also shifted to lower frequencies when the source of the light is moving away from us. And because red light is the longest wavelength electromagnetic radiation that the human eye can see, astronomers say that objects that are moving away from us are redshifted. And throughout this presentation, I will use the term redshift to refer to the motion of galaxies and quasars moving away from us. And almost always those motions away from us will be because of the expansion of the universe. And in fact, that is the key result that is shown here in this figure. This result is showing that as galaxies are more distant, larger distances, they are also moving away from us at larger velocities. That was Hubble's key discovery. And what it means is that the universe is expanding. To help picture why this is the case, you can imagine the 3D universe as a two-dimensional sheet, which is just an approximation, but it's a way that you can imagine how the universe is expanding in time. This is a nice illustration of this that shows the time history of the universe extending horizontally from left to right. The Big Bang, that is the origin of the universe, is over here in this bright flash on the left. The universe underwent a period of very, very rapid expansion early on. This is called inflation. And then after that time, the universe continued to expand, although it expanded at a much slower rate. And as you can see from the size of these circles or the size of this approximately bell-shaped object, the universe actually had a slowing expansion rate as time passed towards the present day. With the exception that in the very most recent universe, you can see that the expansion rate seems to be going up again. And that's the cosmic acceleration that I will come back to. The couple points to notice about this is that at each time, which corresponds to slices in the vertical direction, at each time, the distance between galaxies is increasing because of the expansion of the universe. And because more distant galaxies are separated by a greater amount, they must also be moving faster in order to move farther apart more quickly. And that's why there is a relationship between distance and redshift. And that is what Hubble's diagram here is showing, is that more distant objects are moving away from us more rapidly because the whole volume of the universe is getting larger. And two important aspects of this are first that the relationship between distance and redshift is actually not overwhelmingly obvious on Hubble's diagram. In statistical terms, we would say that these data are pretty noisy. One reason for that is that the measurements were hard to make. Back in Hubble's time, these observations were made with photographic plates that were not as sensitive as modern detectors. But another is that 2 million parsecs is really not that big of a sample of the universe. Even though it sounds like a lot, modern surveys extend many times farther out into space and look much further back in time. At small distances like these, in contrast, the redshift measurements are affected by the random motions of galaxies, in addition to the expansion of the universe, and only sample a very small fraction of the entire age of the universe. The second part I want to emphasize about this diagram is that it only has about 30 measurements on it total, which in modern times is a very, very tiny fraction. I'm going to instead be talking about observations of millions and millions of objects in my presentation in just a few more minutes. And in fact, that's because in the 95 years since this figure was first published, the relationship between distance and measurement, it has remained an important tool of cosmology and has been the subject of many, many additional observations. The slope of this relationship is a measurement of the expansion rate of the universe, and it's called Hubble's constant in honor of Edwin Hubble's work. Hubble's diagram was so critical because it demonstrated conclusively that the universe was not static, which until that time had not been widely believed. And many subsequent studies have used this relationship between distance and redshift to estimate the age and the mass density of the universe. And now we use it to study cosmic acceleration as well. I'd now like to tell you a little bit about how the distance redshift relationship can be such a powerful tool. And in order to do this, imagine that you're on the Earth, which should be pretty easy, and that you throw a ball up into the air, which also should be not that hard to imagine. Here's my diagram of a person throwing a ball up in the air. I looked online to try to find a nice non-copyrighted image of a person throwing a ball in the air. And that wasn't actually as easy as it sounds like it might have been. So instead, I turned to my really extensive graphical skills, and I created this plot all by myself. So here, anyway, this is supposed to evoke the idea that if you throw a ball straight up in the air, just imagine that when it first leaves your hand, that's the fastest that it's going to be moving. And then from that initial speed, as it climbs higher and higher, the speed of it decreases. So in astronomical terms, the expansion rate is decreasing as the distance from your hand increases. The reason that it slows down is almost completely due to the gravitational attraction between the Earth and the ball, especially if we ignore air resistance. And this is analogous to how we expect the expansion rate of the universe to decrease as the universe expands, because the universe has mass in it, and mass causes a gravitational attraction, just like the mass of the Earth causes a gravitational pull on the ball thrown up in the air. If we were doing the same experiment and throwing a ball up in the air on the moon, and we started off with exactly the same initial speed, the ball would slow down more slowly because the force of gravity on the moon is weaker. And that's because the lower mass of the moon is pulling on a ball less powerfully than the Earth does. So if we were on the moon instead of the Earth, then we would have a different relationship between expansion rate and distance. Another nice thing about the moon is that we wouldn't have to worry about air resistance. Although if we were on the moon, we would have to worry about breathing. So this is why scientists like to use thought experiments whenever possible. Thought experiments like this are safer, and they're also a lot cheaper. In any case, in the very local universe where Hubble made his first measurement, he did not see a change in the expansion rate. This is because his data were not good enough to see the effect. But cosmologists knew that the universe was full of matter, and they knew about gravity, so they expected to see a gradual slowing of the expansion rate if they could measure objects at greater distances, and if they could make more accurate measurements. There are two classes of methods that astronomers use to measure distances. One of them is called a standard candle, and the other is called a standard ruler. The basic idea behind both the standard candle and the standard ruler, they're pretty similar, and both are illustrated by this picture. We identify some standard object whose intrinsic properties we know, such that when we observe them at some unknown distance, we can figure out how far away they must be. For example, imagine we knew two candles were identical. If one of them appeared fainter than the other, we would know the fainter one was farther away. Similarly for a standard ruler. If we knew a collection of rulers were identical, we would know that the ones that look smaller, which means they have smaller angular sizes, must be farther away. And using very well calibrated equipment, we could use these tools to estimate distances very well. Since we're observing objects at astronomical distances, we need our standard candles to be very luminous and our standard rulers to be very big. Fortunately, pretty good proxies for both of these exist in nature. The standard candle that we commonly use is a special variety of exploding star called a type 1a supernova, and it's so bright that it becomes as bright or brighter than an entire galaxy. In fact, type 1a supernovae are so intrinsically luminous that astronomers have detected them more than halfway across the universe. The standard ruler that we use is something called the Baryon Acoustic Oscillation Scale, or BAO scale for short. Needless to say, it is much bigger than any ruler you can buy on Earth, and it's even much bigger than our entire galaxy. And I'll explain more about that in a moment. But before I describe some of the results of work on the BAO scale, imagine yourself again on Earth, throwing a ball into the air. We all know to expect that the ball will slow down as it climbs higher and higher. And we know that on Earth, we're unlikely to throw the ball so fast that it's not going to turn around and fall back down towards us. But regardless, we are sure that it's going to slow down because of Earth's gravity. So now imagine your surprise if you threw a ball up into the air, and after it had started to slow down, suddenly it stopped slowing down and started speeding up again and flew away from you faster and faster. What would you say if that happened? Well, I know if I saw that happen, I probably wouldn't believe my eyes. And I would think, oh, well, this violates the laws of physics. Although none of us would really have needed to have taken a physics class to realize that that was weird. Yet amazingly, something very similar to this is what cosmologists discovered that the entire universe is doing. Cosmologists used supernovae to precisely measure the relationship between distance and redshift. And in the late 1990s, about 25 years ago, they discovered that the current expansion rate of the universe is actually speeding up and not slowing down. This was a very difficult measurement to make because the size of the effect was very small compared to the measurement uncertainties. And the researchers knew that a result as extraordinary as a violation of one of the laws of physics would need extraordinary evidence. Nevertheless, the result was corroborated with measurements by two independent teams of researchers. And this is what cosmic acceleration looks like from the perspective of the expansion rate. This is now a figure that shows redshift along the bottom axis. And so redshift is another way of writing the expansion velocity. And the expansion rate of the universe is along the x-axis or the y-axis, along the vertical axis. And then along the top of the diagram, I have added the age of the universe in billions of years. We are currently at redshift 0, and the universe is a little bit over 13 billion years old. That's age since the Big Bang. And what you can see on this diagram is that in the early universe, the expansion rate of the universe was gradually decreasing, going from, say, 80 kilometers per second per million parsecs or megaparsecs to 75 to 70 as the universe went from 2 billion years to 3 billion years to 5 billion years old. And that's exactly what we would expect the universe to have been doing based upon our understanding of gravity. We would expect the expansion rate to be slowing down with time. And so that's why it is so weird that starting around 7 billion years ago, when the universe was almost 7 billion years old, the expansion rate of the universe started to increase again. And this is the cosmic acceleration. This acceleration, starting about a redshift of 0.5 or 0.6, this acceleration is the cosmic acceleration that is a great mystery. And it's an example of the universe literally defying gravity. One immediate suggestion was, well, what about Einstein's cosmological constant? And this is referring back to something that Einstein had included in his theory of general relativity back in 1917. At the time, in 1917, this was before Hubble's measurement that the universe was expanding. And because Einstein knew very well how gravity worked, he thought, well, there must be something in the universe that prevents it from expanding or contracting. He knew that there must be something to offset it because at the time, people thought the universe was static. And so he introduced a constant into his general theory of relativity to keep the universe static and to counterbalance the force of gravity. However, when Hubble discovered that the universe was actually expanding, Einstein said, oh, well, we don't need this cosmological constant anymore. And he threw it out. And in fact, he even called it his greatest blunder. But the discovery of cosmic acceleration in the late 90s showed that the universe actually does need something to defy the law of gravity. And that led people to pull back this idea of the cosmological constant from many decades ago. And the important point I want to make is that while adding a cosmological constant to Einstein's equation does successfully produce the acceleration, it does not say at all what the cosmological constant physically represents. So what is the cosmological constant? Or equivalently, what is causing the acceleration? Well, the short answer is that we don't know. And that's why we built the DESI experiment. This is one of the biggest mysteries in physics, is we don't understand what could be causing the universe to counteract the law of gravity. It implies that there is some additional law of physics that humanity has not yet discovered. A somewhat longer answer is that there are lots of really interesting and plausible ideas. Interesting because no matter what the explanation is, it will expand our knowledge of the physics of the universe. But what we don't have yet is a series of testable predictions that we can, or what we don't have yet is enough data to test different predictions for different models. So one proposed explanation, for example, is that there is some property of space itself that exerts a negative pressure that works in the opposite sense to gravity. In the language of general relativity, that means that there's some intrinsic energy density associated with the vacuum of space that acts like a negative pressure. And this is what people commonly refer to as dark energy. And they call it dark energy because just like with dark matter, we do not see it. Although unlike dark matter, dark energy is increasing the rate of expansion and not decreasing it. But just because you can assign a name to something doesn't mean that you understand what it is. So what is dark energy? There is a plausible route to a solution in what's called quantum field theory. Yet the estimates for this effect from quantum field theory overpredict the value of the cosmological constant by a huge factor, huge even by astronomy standards. So this is not quite a sufficiently satisfying conclusion for most of the community. And so the answer to this mystery might very well be in the quantum realm. And this is an artistic representation of what the quantum realm might look like. It's only an artistic rendition because quantum fluctuations are predicted to be on such small scales that they're not directly observable. They are as small compared to the atom as the atomic scale is to us. So how do we figure out what is causing the expansion? Well, first we need a hypothesis that we can test with data, as that's the cornerstone of science. If an idea can't make predictions that are shown to be accurate, it's not elevated to a scientific theory. In the case of dark energy, there are two main hypotheses. One is that dark energy is a generic property of spacetime, and that is, it is a true cosmological constant. That means that as the universe continues to expand, there will be more space and more volume in the universe, and therefore there will be more negative pressure. This makes a very specific prediction for how cosmic acceleration should change over time. The second option is that dark energy is something else, like a new force of nature. We already know of four fundamental forces of nature: the strong and weak nuclear forces, the electromagnetic force, and gravity. So this hypothetical fifth force is something commonly called quintessence. Many scientists have hypothesized that quintessence could explain cosmic acceleration. Unlike a cosmological constant, the impact of quintessence probably changes with time, and therefore these models predict a different distance redshift relationship than a cosmological constant. The third most prevalent explanation is some modification to Einstein's general theory of relativity. A very simplified version of this idea is that gravity changes from an attractive force to a repulsive force on very large scales, larger even than several million light years. There is some possibility that a modification to general relativity could explain cosmic acceleration, although this explanation was challenged by observations that showed gravity waves travel at the speed of light. Yet even if modifications to gravity do not explain cosmic acceleration, observations such as how galaxies move relative to one another on large scales are great for other tests of general relativity. In summary, all three of these ideas are really exciting. And what we really need are more data and some more tools to test them. At the moment, the best data that we have comes from combining measurements of galaxies, quasars, supernovae, and the cosmic microwave background. I'm going to focus on one of these tools, the standard ruler that I mentioned earlier, called baryon acoustic oscillations, or BAO, as that is the main tool that the DESI project uses. This is an artist's rendition of the baryon acoustic oscillation scale. The BAO scale is a relic from very long ago, from only thousands to hundreds of thousands of years after the Big Bang, so the very early universe. At that time, the universe was so hot and dense that light and normal matter were constantly interacting in what is now called a photon baryon fluid, where baryon is a word that is another word for describing normal matter, or most normal matter. One way to picture the universe at this early time is to try to picture the interior of the sun, except that was what the entire universe was like. If you think about this for a little bit, you'll be glad that once again, we're doing one of those thought experiments and not doing an actual experiment. And you might also be glad that we're 93 million miles away from the sun and not in such a hot, dense plasma. When the universe was really hot and dense, waves were able to travel through this photon baryon fluid, somewhat like the way sound waves travel through the air. All of these waves traveled at the same speed and traveled until the universe suddenly became low enough in density that the photons and baryons decoupled and the waves stopped propagating. This happened about 375,000 years after the Big Bang, when electrons and protons combined together to form neutral atoms. And I'm going to start an animation on the left, and this animation is going to show time since the Big Bang, or redshift here, and it's going to show how the baryon acoustic oscillation scale moves outwards, or it did show how it moves outwards for about the first 375,000 years, and then it stops in the same place. And so now we're watching it again, and right about here, this wave stops moving. And that leaves a constant imprint in the gas density and eventually in the dark matter density at a fixed physical scale that's about 150 megaparsecs, which corresponds to a scale of about 500 million light years. So the density fluctuations in the early universe generated sound waves in the plasma that traveled until recombination at about 375,000 years after the Big Bang. And that left behind an overdensity of matter that we can still measure in the clustering of galaxies and quasars in the universe today. And that becomes our standard ruler, a standard ruler that's 500 million light years long. So the BAO scale is great because this distance scale is very, very tightly fixed, and it will be the same scale at all redshifts. So it makes a great standard ruler. However, there is a disadvantage to it, and that is that it's not easy to measure. There's no giant ruler on the sky that one can take a picture of. The first time this was measured was only back in 2005, so a little bit less than 20 years ago. And that was based upon a lot of work from two large independent teams. One that used a sample of 50,000 galaxies and another that used a sample of over 200,000 galaxies. And this was just to detect it. So even though those samples are huge, that was only able to barely detect or reasonably well detect this signal. Over the course of about 20 years since then, these experiments continued collecting data, and especially the Sloan Digital Sky Survey continued to collect data and eventually collected several million observations. And those gave us a better measurement of the evolution of the universe, but still no sign that we were able to explore these different combinations or different explanations for the nature of dark energy. They certainly made great progress, but we were left with this mystery. And that inspired us to build the DESI project with the Mayall telescope. So now let me show you inside of the dome, and I'll tell you a little bit more about the DESI project itself. Skip that. This is what you would see if you were inside of the Mayall telescope. This is a 4-meter diameter telescope. It has a reflecting mirror that's located about here in the midst of this giant blue horseshoe. When light comes from distant objects, it bounces off of the primary mirror, and then it goes into the instrument that is mounted above the primary mirror at what's called the prime focus. And then we record the data on electronic equipment. I'll go to the next slide, and I'll show you actually all the different instrumentation that we built using a computer model. This is now showing the same view we had before, showing the telescope and the primary mirror here. And now this shows all the instrumentation for DESI. There's a new corrector lens that has, actually it's a corrector lens system that has 6 lenses, each of which are close to a meter across, or about a meter across. It has a focal plane system that has 5,000 fiber optics cables, and therefore we can observe spectra from up to 5,000 objects at a time. And we have an automated positioning system so that we can select which objects we are going to observe for any place on the sky that we want to collect data. And we can very rapidly reconfigure the instrument to go from one area on the sky to the next. And these two features, having the ability to observe 5,000 spectra at a time and to be able to quickly move to a new target, or to new targets, and well, in addition to having extremely sensitive instrumentation, means that we can observe targets at an incredibly high rate. We can sometimes observe as many as 100,000 or even more unique objects in a single night. And in the first year of observations, we were able to observe already over almost 6 million galaxies and quasars, which was several times larger than previous work had done in 20 years of data collection. So it's a really huge step forward to be able to take twice as much data in about 1/20th the time. And that was what the DESI experiment was able to, or is able to, accomplish. Our first data release and our first release of science observations is based upon our first year of observations. So the DESI experiment began in May of 2021, and in the first year, we observed, as I mentioned, about 6 million galaxies and quasars. This is showing the range on the sky that these targets are located in. So this is showing a lot of the northern hemisphere. The light gray region is our full survey footprint. And then these blue or red dots are representing regions that have already had observations in our first year of observations, with this region down here having nearly complete observations. So that's almost our final coverage. And then the blue circles showing places that have one observation so far. The targets that we're observing with these observations are listed here. There are 40 million extragalactic objects in total, ranging from bright galaxies in the nearby universe to what are called luminous red galaxies that are in the somewhat more distant universe. I would note that the redshift scale is along the left-hand side of this cone, and the distance in gigaparsecs, so this is in billions of parsecs, is along the right. So luminous red galaxies are in the range from 0.4 to 1.1 in redshift. And so that's up to a couple gigaparsecs away. Then we have emission line galaxies at even larger distances. And finally, we have 3 million quasars that form our most distant sample. And altogether, we plan to observe about 40 million galaxies and quasars in the first 5 years of the DESI survey. At the moment, we've observed for about 3 years, a little bit over 3 years, and we have about 30 million objects already. So we're making great progress. I'd like to give you now a little bit of a fly-through of these observations. So this is a cool movie that was assembled by a number of my colleagues within the DESI project. This is showing a similar illustration of the large-scale structure of the universe. The scale on here is, probably up to several gigaparsecs. You can imagine that we're down here. This is the local universe, and then we're looking into a cone out into space. And you can see here the large-scale structure of the universe mapped out in the galaxy distribution. So you can see voids and filaments. And now we're going to look kind of edge on and fly into the survey, and we can see the distribution of galaxies as we travel through the universe as seen by DESI. Now we're leaving the nearby universe and going to progressively more distant objects, leaving behind the luminous red galaxies, and then leaving behind the emission line galaxies, and finally getting to the most distant objects and seeing the rare but luminous quasars that form our most distant sample and give us the best view that's ever been obtained of the very highest redshift universe when the universe was only a few billion years old. So now let me show you some of the results that we've obtained from all of these data from our first year of observations. These are our measurements of the baryon acoustic oscillation scale. And the way I'm showing this, and this is thanks to some of my colleagues within the DESI collaboration, is we're showing the size of the BAO scale at a range of different redshifts or a range of different look-back times. So again, the look-back time tells us how long the light has been traveling to us from these objects. Here we have light traveling from only a few billion years, and then progressively greater and greater distances up to the highest redshift sample 11 billion years ago. And so we have very precise measurements of the BAO scale at 7 different points in the expansion history of the universe. And these measurements are pretty closely mapped to a straight line, which is a model for what the distances would be if the universe were well explained by a cosmological constant. And so this is relative to a case with what's called lambda CDM, where lambda is the cosmological constant and CDM refers to the standard so-called cold dark matter model of cosmology. And so these provide us with things like the most precise measurement of the BAO scale that has ever been obtained, or the most precise measurement of the expansion history. And they provide the highest precision measurements of the BAO, especially above a redshift of 0.8. Here's now looking at this from the perspective of the expansion history. What this figure is now showing is 3 versions of the figure I showed towards the beginning of this presentation, which is how the expansion history changes with time, gradually slowing down initially due to gravity, but then accelerating towards the later times. And what this figure is showing, this is now in units, the same units I had before. The dashed line, this line called Planck lambda CDM. Planck refers to the cosmic microwave background experiment Planck that was launched by the European Space Agency. And lambda CDM is referring to the cosmological constant model. And all these different blue lines in the top panel are showing how well the DESI data match that cosmological constant model. And you can see actually that the blue lines are not right on top of it. So that's really quite intriguing. When we change that model and we use something other than a cosmological constant, we use a different value of this parameter W, which I'll talk more about in a moment, or these other parameters here, we can get somewhat of a better match to the data. And so that's suggesting that the data look like they are a little bit of a better match to something other than the standard model. And that's really quite exciting. One of the things that we can do with these data is then extrapolate the measurement of the expansion history to measure what the local value of the expansion history was. So this is the Hubble constant that Hubble was first measuring in the plot that I showed you at the beginning. And in measurements from cosmology, the measurements tend to always give values for this Hubble constant that are in the range of 68 to 69. So in approximately this band here. And for comparison, what I've shown here are 2 measurements that are based upon measurements that are in the local universe that are very similar to the way Hubble did it. And those values are often giving results that are quite a bit larger. So for example, this measurement here of 73 is really quite statistically different from most of these other measurements shown here. But they're measured in 2 quite different ways. This measurement is again based upon using the similar approach to what Hubble used to measure the distance redshift relationship, whereas these measurements are based on extrapolating the expansion history that fit the data at high redshift and seeing what the value is in the local universe where they reach z equals 0 or redshift 0. And so it's very interesting that those don't seem to agree well, and this is something that's called the Hubble tension. The other interesting thing that I wanted to come back to is whether or not dark energy is a constant or not. And one way to describe how the universe might not be following a constant expansion is to instead come up with some other parameterization for how the expansion rate should evolve over time. And two parameters that astronomers use are what are called W naught and WA. These are just variables in an equation that we use to describe how the contribution from dark energy can change over time. In the limit where the contribution from dark energy is not changing, then W naught would be equal to -1 and WA would be equal to 0. And these different colored ellipses or amorphous blobs, those are measurements of these parameters using our data from DESI combined with observations from other projects, including cosmic microwave background observations, and also from various projects that have used supernovae as standard candles to measure the expansion history. If we combine these data together, we can try to find out what model would, or what value of these parameters best matches the model. And those results are somewhat suggesting that W naught of -1 and WA of 0 is not the best match to the data. And in fact, in statistical terms, we see a little bit of a tension at the level of from 2.5 to 3.9 standard deviations away from a model with a pure cosmological constant. And so this is by no means evidence that dark energy is not a cosmological constant, but it is intriguing. This is something that's gotten a lot of us very excited because certainly if this holds up with a much larger data set and further analysis, then this will be a very exciting breakthrough, or would be a very exciting breakthrough into the nature of dark energy. But at this point, we don't consider this level of tension to be proof. We consider this simply to be suggestive, and it certainly has inspired many of us in the cosmology community to spend a lot of time poring over our data and to eagerly await the results that we'll derive from our next set of data, which will be about 5 or 6 times larger than what we used for this particular observation. So let me conclude with just a quick summary of what I've shared with you today. So first, I've told you about DESI and dark energy, and in particular, the DESI survey is the largest spectroscopic survey of the universe that's ever been conducted. The goal of DESI has been to try to understand the nature of dark energy, that is, whatever is causing the accelerating expansion of the universe, since we can't explain it based upon our current understanding of physics. The results from the first year of observations are providing us with a tantalizing hint that dark energy may not be a cosmological constant. And I encourage you to stay tuned for future results based on much more data that will, literally shed more light on this question. So thank you very much for your attention. I want to acknowledge the U.S. Department of Energy and other agencies and foundations that have made the DESI project possible, and acknowledge the many hundreds of people in the DESI collaboration whose work I am describing to you, and also say that the DESI project is grateful to conduct this survey from the land of the Tohono O'odham Nation. So now I'll put my summary back up, and I'd be happy to answer questions. Thank you.
Thank you, Dr. Martini. That was absolutely wonderful. So at this time, for all of our concurrent viewers, we will now have a 15-minute Q&A session. So any questions that you may have, we do ask that you send them now through the live chat. Dr. Martini, I would also like to say that I particularly loved your graphic that you had earlier on. Really nice artistic skills.
Thank you. Yes, you can tell I spent many years in art school.
So, Dr. Martini, while we are waiting for questions to come in, I do have a few questions of my own, as well as I'm sure Dr. McBride does as well. So we'll go ahead and ask you those if that's okay. So first off, you mentioned Einstein's cosmological constant, particularly in relation to his theory of relativity, as well as that being something that was eventually thrown out by him and something considered his greatest blunder. Now having much irony considering the expansion of the universe and things such as that. So could you tell us a bit more? You mentioned quantum field theory, and you mentioned that there was a certain overprediction of that cosmological constant. So could you touch on that a bit more and explain that overprediction?
Sure. So Einstein introduced the cosmological constant to counteract the gravitational force that he knew would otherwise be causing the universe to contract. So he knew that if the universe were static, then the general theory of relativity should cause a contraction. And he introduced the cosmological constant as basically a fudge factor to prevent that contraction from occurring. That there was definitely no physics in that cosmological constant. It was really just merely just an additional term added to the equation to try to explain it. But then subsequent work has, and particularly into quantum mechanics and then into quantum field theory, has revealed that in the quantum realm there is evidence that there's the continual production and destruction of virtual particles on very small scales of 10 to the minus 29, 10 to the minus 30 meters. So many orders of magnitude below even the atomic scale that is already unfathomably small. And various calculations have tried to take what we know of the quantum realm and turn that into a measurement of the amount of, or turn it into a prediction of the amount of negative pressure this kind of boiling of reality on the scales of the quantum would have on the expansion of the universe. And those have very famously over predicted the strength of the dark energy or the vacuum energy of the universe by about 120 orders of magnitude. And so that there is not a good explanation for why that is the case. But I think there are certainly plenty of unknowns in really understanding the quantum realm, just like there is this big unknown in understanding the accelerating expansion of the universe.
Absolutely. I think those unknowns are what fascinate most of us in regards to astronomy and the universe. There's so many things that are yet to be discovered and yet to be known. And really, I think that's where the excitement lies. So I do have one additional question. You mentioned some intrinsic energy density that acts like a negative pressure, and you referred to this as dark energy. So I've read before about dark energy and how dark energy is sometimes referred to as what I would like to know if you also refer to it as this anti-gravity. So is that something that you also use as far as that term, or no?
I don't use the term anti-gravity. And the reason is that in the equations that we have for explaining the impact of this dark energy component on the universe, it really acts much more like a negative pressure than like anti-gravity or antimatter. There are somewhat subtle differences between the idea of negative pressure and anti-gravity. But basically for a negative pressure, the pressure that this exerts on the universe is just the negative of its density in the universe. And so that's a little bit distinct from how we would have a negative gravitational force.
Then lastly, I just have one final question. I may have said that was my final question. So you did touch on certain surveys, and you spoke of how modern surveys, as comparison to older surveys, do extend far beyond, I believe you said around 2 million parsecs. So could you explain exactly or give an approximation of how far modern surveys do extend as compared to those from the past?
Yeah, so the 2 million parsecs was about the limit of the galaxy sample that was in Hubble's original 1929 paper. And 2 million parsecs is, pretty far. The nearest, it's well outside of even our local group of galaxies. For example, let's see, the Andromeda galaxy is a little bit under, it's about a little bit under 1 million parsecs away, if I'm doing my math right in my head. And so this is sampling kind of the local, or Hubble's work was sampling the local volume of the universe. And in comparison, and that was 2 million parsecs was equivalent to sampling out to about 5 or 6 million light years. Well, actually 6 or 7 million light years. And for comparison, when we look at the universe with modern surveys, we're looking at billions of light years. So there's probably a factor of 1,000 or so improvement in the distance that we're able to observe.
So while you were speaking, we had an additional comment roll into our live chat. Wallace Payne, our vice president, wants to know what issues have been encountered with attempting to observe these objects.
We've had a number of challenges associated with doing this experiment. I mean, I think one of the biggest ones was, in order to have this many objects so that we could have a statistically meaningful sample, we needed to make our survey super sensitive so that we could observe large numbers of faint objects in still a relatively finite amount of time. And so we had lots of challenges to overcome in order to ensure that our instrumentation was as sensitive as possible. From an instrumentation standpoint, I think one of the big challenges we've had is that sometimes pieces of the instrument stop functioning the way they're supposed to, and so we have to figure out why, and we have to conduct repairs if it's possible to repair them. And so we have a really dedicated group of scientists and engineers who are constantly working with the instrument to keep it running, and that includes both the staff at the Kitt Peak National Observatory, and it also includes many scientists who are part of the collaboration and who are around the world. Another challenge, we've had a number of other challenges as well. Like, for example, there was a really pretty horrible forest fire that swept over Kitt Peak National Observatory a couple years ago. And it was only thanks to really heroic efforts by the firefighting teams that there was not significant damage to the DESI experiment. There were several buildings were destroyed, and some observatories did suffer some damage, but fortunately our facility was spared the worst of it. But then we were left without, because the telephone and communications poles all burned in the fire, we were left without internet and power on site for quite a few months. And so we ran off of generators, and we were basically carrying our data down on portable hard drives to the nearest internet link. So we've had a number of challenges, and not even mentioning the fact that we were originally going to start the experiment in mid to late 2020, and there was so COVID was also a challenge for us.
Dr. McBride, do you have any questions?
Well, I guess one question I like to get a perspective on is maybe from a younger member in the audience that's listened to your talk, and where would they go in terms of courses to get into your field? Like, what were the core courses that a student should sort of focus in if they've just listened to your talk and they're completely enthralled and they say, this is what I want to do? What trajectory would you send them on?
Well, I can certainly describe my education trajectory. So I grew up in Philadelphia, Pennsylvania, and I went to high school and college there. And certainly in high school, I took lots of math and science classes. And then I went to Temple University, where I got an undergraduate degree in physics and I minored in mathematics. And I knew that I would need to have a really good understanding of physics and math to answer these kinds of questions. From a very young age, I was really excited about the universe and how the universe works. And I was very influenced by books like Stephen Hawking's book, A Brief History of Time. And one of the things I really loved about that book was not just the way it explained all of these great mysteries, but also it really made me feel like, well, somebody who knew a little bit more math, or maybe a lot more math and physics than I did, you could actually make progress on these, and like real people could do this. And so that really inspired me to take physics and math classes. And then when I got to college, I started pursuing research opportunities. I did some research in physics, and then I also had some astronomy research experiences. And that led me to graduate school and to a PhD. And then subsequently, I've continued in the field doing research, and now I'm on the faculty at Ohio State.
Fantastic.
So, Dr. Martini, you mentioned Stephen Hawking's book. I've also read that book, as well as a few of his others, and it is definitely a good read. So, 2 thumbs up for that.
Yes, I highly recommend it for anyone who is interested in questions like the universe, or also one of my other favorite topics, which is black holes. It is great to read, and it's very approachable. I read it in high school, so you definitely do not need to be an expert in math and physics in order to understand that book. You just have to be excited and enthusiastic.
Fun fact, I believe I also actually read that book for the first time in high school.
Yeah.
So it is now 7:02 p.m. As I don't see any more questions coming into our live chat at this time, just for a final question for you. So you did, as we've discussed, mention dark energy. Now, would you say that dark energy is a new force of nature, or some other hypothetical fifth force? Is that your key front point when it comes to dark energy?
Yeah, that's a really good question. So I think the two most the two plausible explanations are that it's either something about the structure of the universe itself at the quantum level that's causing a cosmological constant like uh, effect, or it is a fifth force of nature that is causing this accelerating expansion, and it's just something that has become more important in the universe at what we call late times, meaning in the last 3 to 5 billion years or so. And I I really try hard not to have a preferred explanation. I really want to be driven by what the data ultimately show us. And so I like both of those explanations. I don't know if I would call the quantum realm explanation a fifth force of nature. It's really more maybe of an incomplete merger of quantum mechanics and general relativity. So either way, though, there's clearly quite a bit about our universe that we don't understand, and I find that really fascinating.
I think we all find that really fascinating. So this has just been an absolutely wonderful lesson. We've really enjoyed your talk. I think I speak for myself as well as Dr. McBride and all of our live concurrent viewers, as well as those that will view this afterwards. We've really all benefited from the time that you've dedicated to us this evening, and I'm sure we're all far more interested now in cosmic acceleration. I know I am personally, so thank you.
Well, thank you very much for the invitation to speak with you and speak with the group. It's been really exciting, and I think this is a wonderful program that you have at Marshall, and I am excited to be able to share some of my excitement with all of you. So, thank you.
Thanks again. We, like Hannah said, we really do appreciate it, and very good talk. Thank you.
Thank you.